Hello. So today's session that we start with the discussion of collinear variables. We finished our topic in the previous session about post-regression diagnostics, and we found several tests that we did on simple OLS, and we understood how to diagnose a model. Now today we are selecting one of the problem, and we are going in detail how to check it in detail and what are the possible types of that problem and how to detect it and what are the possible remedials. So first of all, we'll start with today's topic is the collinear variable. So it will occur when your independent variables are collinear to each other. So collinear is collinear word can easily be understood by other word means correlated. So if independent variables are correlated, it will lead to some problems which are discussed here. So first of all, we will define multicollinearity. So its literal meaning is correlation between independent variables. So if we define it, try to define it in detail. So it can be a situation whereby two or more independent variables are influencing each other. Means that two or more than two variables are influencing or related to each other, which are actually assumed to be independent of each other in a regression framework. And when they're influencing each other, they are actually also determining the dependent variable. Means they were actually selected to influence the dependent variable, but in reality they are also determining each other, such that it becomes difficult to isolate the effect of single variable. Means they first hand they were selected to affect the dependent variable, but second stage they are also affecting each other. It means it will become difficult to isolate the effect of independent variable on a dependent variable within the OLS or simple regression framework that we discussed. So within this regression model, if first independent variable is affecting dependent variable and second independent variable is affecting the variable, so it means and they are affecting each other too. So to isolate the effect of x1 on y and x2 on y will be very difficult. So the consequence of this is creation of apparent significance. Means that the model will be apparently significant, means the overall model will be good enough and it will be explaining the changes in the y, but there will be more noise. The model will have noise. Noise means that the individual variables are not significant. Means uh, overall model will look like it is working well, but since the variables are jumbled together, they are complicated in terms of playing their role. So when we look at the OLS will propose that they are not useful, but overall model will propose that the model is good. So there will be a clash of outcomes. Overall tests are saying that model is good, but individual tests are saying model is noisy. So similar thing, a similar example can be understood by one Quran ayat from Quran Majid that said that, oh, you have believed, do not approach prayer while you are intoxicated until you know what you are saying. It means that the prayer is an individual ritual. So you have to stand in front of Allah for 5 times a day. So for that function to be performed well, you need to make sure you are not influenced by other things. Means intoxication. So Allah has commanded to indulge into prayers when you are in command of yourself. Otherwise, it will be a noise. So this way we define the concept of multicollinearity. So next is we will discuss with an example. So consider a simple model that we built. So simple model is y dependent variable is equal to intercept plus slope 1 with variable 1 and slope 2 with variable 2 and error term. This is a simple model that we try to estimate, and we have two independent variables and one dependent variable. But we ignored that there is another relation that exists in reality, that is x1 is equal to constant or a slope into x2, means the way x1 is also related to x2, means there is a auxiliary relationship that we ignored, or we assumed that it does not exist, or we don't know in reality, maybe. So now when we isolate the effect of x2 on y, so if you want to isolate the effect of x2 on y, we need to calculate the derivative. And when we calculate the derivative, so the derivative of y with respect to change in x2 will be what it will be. So it will be b1c and b2. So how we know that it is b1c? Because when we put c x2 here, it is b1c x2 here. So when we take a derivative, x2 is here and x2 is here. So b1c plus b2, which is not equal to b2 that it should be if we assume that the auxiliary regression does not exist. So it means this and this there is an inequality. So the hypothetical effect was b2, and the actual effect is b1c plus b2. So this equality is not possible, and this equality will not happen even if we increase the sample size. Only it is only possible if luckily b1 is 0, means the b1 is 0 or c is equal to 0. So b1 0 means that x1 is insignificant, or c0 means there is no relation between x1 and x2. So the hypothesized coefficient, which was b2, and the actual coefficient, which is b1c plus b2, are not same. It means that the regression is giving us biased results. The hypothetical results are not similar to the actual results, or if you, in other words, you can say the sample results are not equal to the population results that should have been. So multicollinearity leads to biasness in the coefficients. So not accounting and further, if we assume that this relation does not exist, so not accounting for the cross independent variable correlation may lead to erroneous predictions and may cost lives. So it means if we don't account for this multicollinearity, and in real life we make a policy out of this model, it will give us wrong results. And if it is a biostatistics or any life sciences related subject, so it might lead to it might cost a life, because the prediction was terribly wrong. Okay, so let's go with further. So similarly, if we calculate the standard error of beta 2 means the standard error of let's simplify, we use this b2. So standard error of b2 is overall standard deviation of the model, overall variance of the model, divided by deviations in variable x2 whole square and 1 minus r12 whole square. So it is telling us that when there are two variables in the model, the variance calculation formula is such. So the formula is that the standard error of a slope 2 depends upon the variance of the model divided by variation in the x2 variable and the correlation between x1 and x2. So it means if the two independent variables are correlated, which is R12, then the variance of the model will rise. It will increase because the bigger the number, and this becomes smaller, and overall it will become bigger. So it means increase in correlation leads to increase in standard error, which will make our variable insignificant in the estimation results. So we already know the significance depends upon larger value of slope and smaller value of standard error. So it means multicollinearity also increases standard deviation. Secondly, the another problem is that if if the coefficient which is B2 into C, P1 into C. So if the B1 into C is bigger in magnitude and opposite in size as compared to B2, okay, that is shown in the equation below. So what will happen? It will make variable show opposite signs. That's another consequence. So what? So that's another consequence that the multicollinearity creates. So the it will we have discussed that regression multicollinearity has these problems. Now we go towards the derivation of OLS, and we'll see where in the derivation the concept of multicollinearity plays its role. So consider the model of OLS using a matrix approach. So we have y as an independent variable and x is a matrix of all the independent variable, and the first variable is a constant, so that the first column gives us intercept. So y is equal to beta x plus e. So this is the matrix form. Now we open the matrix form. We have y is a matrix of y1 to yn. So there are n observations. So it's a y matrix of n rows and one column. So it's a one column n rows matrix of y, and x is a k by n matrix. K is the number of variables and n is number of observations. So first one will be 1 1 1 1 1 as a constant, and second one will be x2, and the last one will be xk, and the last observation will be xkn. So there are k plus 1 variables. First variable will be constant and remaining k are variables, and there are n observations. Multiply by the beta, and it has a beta hat because we are talking about sample, and then error term has n observations, so error term 1 till error term n. So this is a matrix form of the regression model. Now we'll try to now we need to solve the beta, solve it for beta. So beta is itself is a matrix. So if we open we solve it, we need to isolate error term first and move others on the other side. So error term matrix is equal to y matrix minus x matrix plus beta. Now we need, if we need to solve it, we need to first of all multiply it with its created a square form. So in a matrix, the square form if you need to calculate a square form, you need to take a transpose. So error term transpose into error term is equal to y minus x transpose beta whole transpose y minus x transpose beta. So we have actually squared this matrix. Why? Because the only way to find beta is to minimize E prime E transpose E matrix. So the betas are calculated by minimizing the squared residuals. So first of all, we have to calculate the square form. So this is the equation that is showing the square form, and now we open it up. So error term transpose error term is y transpose y minus 2 beta x transpose y plus beta x transpose x beta. So we have this relationship, and let's see if anything is left. Okay. So now we know that beta prime beta is a constant matrix, so its transform is equal to transpose. So we will now take a derivative and solve it. So we need to take a derivative of error term square with respect to beta. So what is an objective here? We need to find the value of beta where error term square is minimum. So to calculate the minimum, we need to calculate the derivative. So derivative of error term square divided by beta is change in error prime error transpose error divided by beta. So that will be equal to 2 x transpose y plus 2 x transpose x beta. So because that this 2 comes because there were 2 betas and it's beta square, so 2 came out from here, and this 2 is because there was 2 beta here and 2 came out, and beta is cancelled because of the derivative. So now if we put it equal to 0 to optimize the error term, we can calculate x prime x beta is equal to x prime y. And then beta will be equal to x prime y divided by x prime x. And then beta will be equal to x prime x inverse, because it will go on the top, and and x prime y. Or x prime means x transpose y. So now we need to calculate inverse. The formula is x transpose x inverse is equal to adjoint of x transpose x and determinant of x transpose x. So the problem comes here. So if the independent variables are correlated with each other, and we know that determinant, so I can, for that we need to calculate the determinant of denominator, and here the terminology need to be understood. The rank of the matrix shows how many rows and columns are independent to each other. So the determinant actually is depends upon the rank of the matrix. If the rank is high, the determinant will be nearer to 1. Okay, so so the rank of the matrix shows how many rows independent of each other. If all the independent variables are uncorrelated, the rank will be equal to the number of variables. So it's a full rank. It means if all the variables are independent, then the rank is full rank, and they are not correlated. So here, more the variables are uncorrelated with each other, the higher will be the rank, which will cause higher value of determinant. Means if x1, x2, and xk are independent to each other, then the rank will be higher and the determinant will be higher. And so if there is multicollinearity in the model, then the rank will be smaller, means variables are collinear, which will lead to smaller determinant, which will lead to smaller value of beta. So what it is saying here is, if the independent variables are collinear, the determinant will be smaller, and if the determinant is smaller, the beta will be determinant is smaller. It means inverse is bigger. It means beta is different than the reality. The answer will be not precise that it should be. So it means that we need to calculate the value of x prime x determinant. So this test will go through when we cover the regression diagnostic. But if the matrix is full rank, then x prime x determinant will be nearer to 1. It means that there is no multicollinearity. If there is collinearity, then the answer will be less than 1. And if the answer is 0, it means there is too high multicollinearity, and that is a problem. Too high multicollinearity means that this will become 0 and inverse will become infinity, and it means beta will become infinity. And in data analysis, infinity means uncalculatable. So it means if there is perfect multicollinearity, the regression will not give us any results, and we will be clueless and what is the reason behind it. The main reason is that there is too high multicollinearity. Now we will continue towards the discussion of different types of multicollinearity and what are their symptoms, and what is the source. So first common problem that is similar to multicollinearity is micronumerosity. So micronumerosity has similar symptoms than multicollinearity, so I have added it as a part of multicollinearity. So the symptom of micronumerosity is that there will be insignificant variables. The overall F test will be insignificant. The R square will be very low. So if the model is affected by micronumerosity, the way to find out is that your variables will be insignificant. None of the variables will be able to explain the model properly, and overall model is also imprecise or insignificant. Means overall model is also saying that it is not able to explain the changes in the dependent variable, and R square is very low, means the independent variable are literally useless. So the source is, what is the possible source? The data is not comprehensive enough to estimate the theory at hand. It means that the theory that you are trying to measure is a, for that the data is not big enough, or data does not include the relevant observations that can create a comparison. If you're trying to estimate a research on determinants of student failure and you haven't included the students who got F grade in the exam, and you collected data from 500 students, it means you haven't created any example of failure. So how your model will pick up the determinants of failure? So it will not be able to, it will explain the determinants of success, but it will not explain the determinants of failure. So the results will be will lead to micronumerosity in terms of theory. So then there is another type, that is weak multicollinearity, a weak form of multicollinearity. So what are the symptoms? That the variable will be insignificant. How we check insignificance? That their p values or prob is greater than 0.05. So variables are insignificant, and there is a significant F test, means overall model is fit and R squares are very high. So these are the symptoms, that overall model is saying very good and the variables are saying very bad. So there is a clash of model interpretations. So there's a conflict. So need to decide which to select. So the main reason or source can be you have selected too many independent variables and some of them are similar to each other. So if there are too many variables, you will end up in creating weak multicollinearity. Then there is a theoretical moderation. Theoretical moderation comes, the symptom is if you add a cross product in the two variables which were actually insignificant, the model improves, means they become significant. So if the cross product improves the problem, solves the problem, it means there is theoretical moderation. And what is a source? Source is that your independent are maybe catalyst of each other. They are influencing the way other variables are actually affecting. So they are theoretically catalyst. So we will cover it up later. So then there is a strong multicollinearity. What is strong multicollinearity? It means that your variables are actually significant, but they have opposite signs. Means your overall model is good, variables are significant, but when you compare it with the theoretical signs, and you found out that the signs are opposite. So it happens when there is very high correlation among the independent variables, and or there is a common causal variable. So the common causal variable is comes under time series econometrics. So we will cover it up later when we focus on time series. And in the cross section econometrics that we are studying right now, it will be because that the independent variables are very similar to each other. Last is perfect multicollinearity. So perfect multicollinearity is symptom is that regression will not run unless you drop the problematic variable. In some regression softwares, some statistical softwares, it drops the problematic variable and estimates the regression. But in some other softwares, it does not estimate it. It gives an error that the matrix is not invertible, means the determinants is 0 and the beta is infinity. So regression cannot give answer in infinity. So it will stop and give an error. So perfect multicollinearity will come when two or more independent variables are exactly identical to each other. So the only way to do the reason is that the two independent variables are identical to each other. So this is the way we can distinguish between different types of multicollinearity.